Hello and welcome to our channel. I'm Hansa, and in this video you'll find a question from calculus. In this question you will find the combination of concepts from different topics like mean value theorem, monotonicity, and definite integration. Let's see the question and how to solve it. This question is also important for those students who are preparing for IIT. So let's see how we can solve the question. First of all, what is the question? The question says that consider the function fx and another function g. As you can see, it is defined from closed 1 to infinity to r such that. So there are two conditions which are provided for the function g and f. What are those two conditions? The first condition says that g is differentiable with the continuous derivative. So g is already a differentiable function and it has a continuous derivative. Second, f is continuous and the function. Now see, a new function is there, h, which is defined from 1 to infinity to r, and h of x has this value, which is g dash of x, f of g of x, is a non-decreasing function. It is a non-decreasing function. Now denote an as k sigma k is from 1 to n h of x, k. What we need to prove here is an plus 1 minus h of 1 is less than or equals to this integral, which in turn is less than or equals to an for all n greater than equals to 1. So now I'll start solving the question. How we are going to solve the question, let us see. I'll make use of all the information that they have given for proceeding. Like the first information that they have provided us is g is differentiable and a continuous derivative and having a continuous derivative. Second, f is continuous. F is continuous and the function h is this one. So I'm going to start my question from here. What we have is h of x is equals to g dash of x, f of g of x. You can see that basically h of x is nothing but the product of two continuous functions. The derivative of g is a continuous derivative. G has a continuous derivative, so g dash is definitely a continuous function. F of g of x is also continuous. Now, since h is the product of two continuous functions, I can say that h is a continuous function. And further, since h is a continuous function, I can say that h of x is nothing but a derivative of a function. What do you mean by derivative of a function? Derivative of a function means that this function definitely has an antiderivative. You can integrate this function, and I'm just assuming that the antiderivative of this function h of x is nothing but capital F of x. So f of x ko what we have assumed is integral h of x, or you can say that f dash of x ko I'm assuming to be equals to f of x. So we have f of x as the antiderivative of h of x. This is what I'm taking in the question. Now look at the question or look at the function f of x right now. We know that f of x is derivable and it has the derivative h of x. Since capital F of x is derivable, I can say that it is continuous plus derivable. That's why it is possible to have a value ck. I'm just applying the Lagrange's mean value theorem here, which is applicable for a continuous and derivable function. But in which interval are we applying it? So I'm just selecting some interval. Let's see which interval I'm going to take. So I'm going to select some interval which will be from closed interval k to k plus 1. I'm taking one length interval over here, k to k plus 1. So if you apply Lagrange's mean value theorem to this function in this interval, you can say that definitely we are going to find out some ck belonging to open interval k to k plus 1 such that Lagrange's mean value theorem says that f of k plus 1 minus f of k upon k plus 1 minus k, which in turn is going to be 1. So I'm not writing it, is going to be equals to f dash of ck. F dash of ck means h of ck. H of ck. Now see, what we have derived here is a relation for h of ck in terms of an entirely new function capital F of x. I have written that for some ck belonging to k say k plus 1, we will have h of ck value is equals to f of k plus 1 minus f of k. What I'm going to do next, see in the question they have given that h of x is a non-decreasing function. H of x is a non-decreasing function means because it is a non-decreasing function, I can definitely say that h of ck is going to be greater than or equals to h of k plus 1. I'm just comparing the functional value of h in this interval. And similarly, h of ck is definitely going to be less than or equals to h of k. But what is h of ck? H of ck, when you write its value from the first equation, you can write it as capital F of k plus 1 minus f of k less than or equals to h of k, and here hk plus 1. See, they have provided us in the question the value of an. They have defined an as this one. They have defined an is equals to sigma case from 1 to n hk. I'm going to make use of this information now. Let us rewrite h of k in terms of an. But creating an means you need a sigma sign. You need a sigma sign means now what will be my next step after this? I'm going to put sigma all the three sides. It will be sigma h of k plus 1, where we will take k from 1 to n, less than or equals to, here you can see that a kind of telescopic series we are getting in the middle, f of k plus 1 minus f of k, and less than or equals to extreme right way we are going to get k is equals to 1 to n h of k. According to the question, I can replace this value by an. So I'm going to replace it with an. So let's replace it with an. What about the middle term? When you keep putting the values of k 1, 2, 3, 4 up to n, you will end up getting only the last term f of n plus 1. And from the first term, only f of 1 will be left out. Rest all the terms are going to cancel because of the telescopic nature of the series. And it is greater than or equals to, now what should I write here? This is h2, h3 and so on. So I can say that this is nothing but an plus 1. But now the one term is missing. What is that one term? H of 1 is not being created in the sigma. Because it is not created, I have subtracted it from an plus 1. So now you can see that what we have written is an plus 1 minus h of 1 is less than or equals to f of n plus 1 minus f1 less than or equals to an. But what is the use of this one? From here itself, actually, we are going to prove what we need to prove in the question. That is, let us go back to the question and see once again what we need to prove here is this thing. Integral g1 to gn plus 1 small fx dx is greater than or equals to left and less than or equals to right. So you must have noticed that these two terms that we have already created. I just need to create this one, and in the very next step you will find that we are able to create it very easily. Why? Because first of all, f of n plus 1 minus f of 1. This indicates nothing but integral 1 to n plus 1, integral 1 to n plus 1, h of x dx, right? Because h ka antiderivative is f. So obviously after integrating and putting these limits, we will be able to create this thing. It is less than or equals to an, greater than or equals to an plus 1 minus h of 1. But what is h of x? According to the question, I can rewrite h of x, and h of x as they have given is nothing but g dash of x, f of g of x. This is the function that they have provided us. Less than or equals to an, greater than or equals to an plus 1 minus h of 1. Going to the next step, because I want to create exactly that form which is given in the question. So observe this integrand, and you can notice that in this integrand, I can replace g of x with a new variable t. But if you are putting g of x as t, then g dash of x is going to be, or g dash of x dx is going to become dt. Let us keep these values, and then you will find that what we are getting is a n plus 1 minus h of 1 less than or equals to integral. The limits are also going to change. You can see the lower limit has now become g of 1. The upper limit have now become g of n plus 1. F of g of x will now be replaced with f of t. G dash of dx will be replaced with dt less than or equals to an. Using the property of definite integration, I can replace this t and this t with another variable, and I'm going to replace it with small x. Why I'm going to replace it with small x? Because this is what we want in the question. As you can see, I'm just going to show it back. What we wanted to prove in the question was in the form of x. So just using the properties of definite integration, I replaced x with t, and hence we have proved the question. So here is the proof. This is how we have proved the question. I hope you enjoyed the question. Thanks for watching. Bye-bye for now.